Welcome to topic 2 of data science. And in this topic, we're looking at the 4 A's or SQA's of data. I humorously call them the 4 SQA's of data because I haven't really encountered these outside of this particular unit, but they group together quite nicely anyway. So the first of the 4 A's is data architecture. Okay, so I've just put a little quote down there. The main focus of data science is the extraction of knowledge from data. Okay, so what is data architecture? So data architecture is composed of models, policies, rules, or standards that govern which data is collected, how the data is stored, arranged, integrated, and put to use in data systems and organizations. And this involves routing and then organizing data. Okay, so to route and then to organize data. So we have a graphic that I borrowed using fair usage for education purposes from the internet. And we have here some data science system, some data visualization system here, which is linked to some servers, which is then linked out to, I'm guessing this light bulb is some sort of AI system or some sort of idea generation system, which is then linked eventually into the human mind. Okay, so this is showing you how the human mind can be integrated via data architecture into this. So this whole system would be data architecture. How is the data routed, organized? Where is it stored? What servers is it stored on? And how does it get from the servers in and out? So it's a fairly simple concept. Now, I found some definitions of data architecture, but I need to fill in some of the references. So I will do this at some point. I tidied these up the other day. So I've got who said it, but I need to find out when exactly they said it, and I will fill this in as this course goes on. I think it's unfair to put a reference in and not say when these were. So first of all, the first definition is from Eichen 2017, and he says data architecture is a common vocabulary for expressing integrated requirements, ensuring that data assets are stored, arranged, managed, and used in systems in support of an organizational strategy. And we can probably gather that Mr. Eichen is, or Ms. Eichen, is from the United States due to the use of the IZ in organization. So Keith D. Foote says that data architecture is a set of rules, policies, and models that determine what kind of data gets collected, how it gets used, processed, and stored within a database system. Data architecture is using data effectively and built on a foundation of business requirements, from Sven Bloomberg et al. And finally, Dalmule and Davenport from the Harvard Business Review said data architecture describes how data is collected, stored, transformed, distributed, and consumed. It includes rules governing structured formats such as databases and file systems, and the systems for connecting data with the business process that consume it. Somewhat of a little bit more of a boring description there. So really, in terms of the SQA, data architecture is the routing and organizing of data inside a data system. So the next A of data is data acquisition. Okay, data acquisition. And data acquisition can also be known as collecting data. So I've got here a little graphic of an idealized data science workflow. And in there we have the stages of data science. Now, problem identification could be asking the right question, planning. Then we have this stage, data acquisition. So what actually is data acquisition? Data acquisition is collecting data. Okay. Now, the very important thing that you have to think is if you have some data, in a different department in the current organization you work for. That data is then given to you. That is not data acquisition. Okay, data acquisition is only data acquisition if the data comes from outside the organization. Okay, it must be external data. Okay, if the data comes from a different place and you bring it into your system, then that is data acquisition. You have acquired that data. Okay. Now, with the advent of data science and predictive analytics, many organizations have come to the realization that enterprise data that they already have must be fused with external data to enable and scale a digital business transformation. So it's all very well having a lot of data on people's postcodes, and you might want to somehow bring in some map data so that you could geolocate those postcodes. So you would have to acquire, you'd have to bring in some extra data to use in your analysis. So processing for identifying, sourcing, understanding, assessing, and ingesting such data must be developed. So 2 points of confusion surround data acquisition. The first is that data acquisition is sometimes used to refer to data that the organization's already got, and that's wrong. That's not data acquisition, okay? So data that's already required, that's actually called data ingestion. All right, if you already have some data and you're moving it from one system into another, that's called data ingestion, okay? Data acquisition is when you're getting data from outside the organization and bringing it inside the organization. Okay, so data ingestion is just the process of copying the data from one environment to another. It's much narrower than data acquisition. So fairly simple concept, data acquisition. Right, data archiving. Now I have heard some people say this like archiving, okay? So it's data archiving, like a K here. And this is storage of data for future use. So data archiving is collecting data in a form that maximizes reusability and future reusability. The main challenge of data archiving is anticipating the future uses of the data. So in Lab 2, we looked at the IRIS dataset in R, and the IRIS dataset was originally collected in the 1930s. So, 90 years ago, nearly 100 years ago, that was collected. But it was obviously collected, the plants were measured, and accurate records were taken in such a way that it was well preserved. So we were able to move it into RStudio as a built-in data set that we can use to do some analysis on. So that was well archived data. Another thing to think about is whenever you collect data and archive it, it's quite important to have an understanding of how you're going to store that data and is that data going to be needed in the future, trying to anticipate what will be needed. And they say in this course anyway that the main challenge is anticipating the future uses of the data. Now, if you think, the Romans were very good at data archiving. They left behind a lot of records written in Latin that we can get historians to read today, stone tablets and buildings and things, and they built roads and aqueducts and other things. What have the Romans ever done for us? So they they were quite good at data archiving, and with a little bit of research, we could probably tell you who the third emperor of the Roman Empire was, what his name was, where he was from, how long he was the Caesar for, what did he do, what laws, who organized Hadrian's Wall, where did they get the stones from? Stuart's saying in the chat, Nero. Was it really Nero? See the third emperor, the Roman Empire. Interesting. Yes. Oh, very good. Right. So there you go. So that's good data archiving, isn't it? Because that was 2,000 years ago, roughly, that happened. And we're still able to just look up and find out what happened there. Now, after the fall of Rome in around the year 450, Fred's saying Caligula. I don't know if anyone's seen that film. It's probably beyond the scope of this course. There's a film about him though. You put me off. Right. So yeah, Caligula. A good film about him, depending on your taste. After the fall of Rome in around about the year 450, not too long after, we entered a period called the Dark Ages. And the reason, or one of the reasons we call it the Dark Ages, is because we don't really know entirely what went on then. So that would be a bad use of data archiving. Okay, we don't really know what happened then. All right, so if you're going to keep records of data, it's important to store it in a way that it can be reused in the future. So for example, let's say we archived a lot of data, a lot of records and things, and we archived it all in Scottish Gaelic. And then 1,000 years into the future, we were all trying to figure out how to read it. It might be quite difficult. Okay. Or if let's say we kept all the records in Polish or in French, this will make it more of a challenge to read. Now, don't want to try and sound like an English imperialist. Maybe French will be the main language in the future. Maybe it's a bad idea to archive stuff in English. The Romans certainly knew what they were doing by writing everything in Latin, so it was easily read in the future, and we can figure out. So it's quite a simple concept, this data archiving, maximize reusability, and the challenge is to anticipate what might be needed in the future. So just like the iris data set, you might later on today, if the weather cheers up, end up out in your garden with a measuring tape, measuring various plants and things. And then there could be a nuclear apocalypse, and the only record of plants might be your study that you did of your garden, the only record of plants in Edinburgh. So if you did that properly, you took photographs and you measured everything and you stored the data properly, then we might have to use that data to rebuild society. Right, what else is involved? So data archiving is the process of moving data that's no longer actively used to a separate storage device for long-term retention. So I think the United States keep a lot of things in various time capsules in the desert, buried, in case they blow themselves up. So we need to try and think about what we're going to do with data in the future. So archived data consists of older data that remains important. And you can think of this being data being archived like a museum archive. So you have specialists at the museum that know about how to keep all old things and catalogue them and put them in order and put them in more order and put them in databases and look them up, and then they can go and get them. That's the important thing. If we archived all of the museum's collection and we just piled it up in a room and didn't organize it in any way, and then someone came in and said, "Oh, do you have one of those, do you have one of those arrowheads from the Battle of Bannockburn around?" You'd be like, "Yeah, hang on, let's just have a look through this box here and see if we've got one lying about." So archive data is usually on a lower cost tier of storage to reduce primary storage consumption. We can do things like create backup tapes and create zip files. So those three were fairly straightforward. We had data architecture, data acquisition, and data archiving. This, the last A of data, the fourth, is a little bit more detailed. This is the most kind of detailed of the four. So we have data analysis. Data mining is the practice of examining a large pre-existing data set to try and find new information. So just like you would mine for gold in the ground, you're looking for new gold in existing ground. So data mining is the same. You're looking for new information from existing data. Now, I said in part one that there were 5 stages to data science. However, this here is actually 3 stages, and I'll try and explain why that is. So if you think, I said the first stage of data science was planning and asking the right question. But when you think about that, that's not really applied data science, is it? We could ask the right question about anything. So that the first stage here we have is data preparation, but we add on a little stage before this where we plan and we ask the right question. After we prepare the data, which is the most complex stage, so cleaning the data, doing the data acquisition, getting the data ready, we can then move to data analysis and data mining. Okay, this is the middle stage. And sometimes we'll have to revisit the preparation stage and come back to this stage. Maybe even revisit the question stage, go through preparation again, come back here. And then there is the presentation of the results. Okay, so if that's stage 4, there is another stage after this. And that stage, I said, was acting on the results. But if you think about it, you know, planning and acting on the results isn't really applied data science. Okay, that's why we have these 3 stages here. Okay, so we can add a stage on before and a stage on at the end where we do something about the results. So what is data analysis then? Data analysis is a lot of different types of analysis we can do on data. So data analysis involves using data samples to make inferences about that data. And an example could be employment figures or population age statistics. So, you know, let's look at the employment figures 2 years ago, and let's look at the employment figures now. What analysis can we draw from those figures? Okay, what can we say about that? You know, what effect has the recent social and economic climate had on those figures? How are they influenced? Population age statistics, you know, how many people are there of each age bracket? Do we have more old people? Do we have more young people? How many? Where do they live? Things like that. So some different types of analysis. Descriptive analysis is when you look at data and you generate insights from findings. And this is a very common type of analysis. Then we have prescriptive analysis. So creating a prescription. And this is the area of data analytics that focuses on finding the best course of action in a scenario given the available data. So much like a GP, a doctor would write a prescription, they're finding the best course of action given the available data. Then we have predictive analysis. So this is the branch of advanced analytics that's used to make predictions about unknown future events. So what data do we have and what can we say we predict is going to happen with that data? So here's an example called factor analysis. Now, we have some variables here: income, education, occupation, and some different factors. Okay, factor analysis just uses some simple arithmetic operations. The relationship of each variable to the underlying factor is expressed by that factor loading. So here's an example here where we have the iris data set, and we have the three different types of iris: setosa, versicolor, and virginica. Okay, we can use that to analyze these. Machine learning is the scientific study of algorithms and statistical models used to perform a specific task without explicit instructions on patterns. So it's about creating some sort of an algorithm to allow the machine to learn how to respond or perform a specific task, but without having direct instructions about that task. So we can try and train a machine with data using training data to try and help that machine respond. And this is seen as a subset of artificial intelligence. And there are some concepts in machine learning. Machine learning is also referred to as predictive analytics. And these have a wide variety of applications. One simple one to think about is email filtering. Okay, so we want to put into the junk anything probably about, making lots of money with Bitcoin or something that's likely to be junk email, So we want to try and train our email server to identify which one's junk and which one's not. So if we can, and the other thing is, what's junk to you is not to me. So it has to try to have some sort of learning capability to try and figure out. Also, as new trends appear, like for example vaccines or something, new junk mail related to that will appear. So we have to try and figure out, is it spam or is it inbox? So that's a machine learning problem. And apparently it's difficult to develop a conventional algorithm to perform this task. As you know, people will often use the phrase, have you checked in the junk folder to see if the email's there? And it might be. So machine learning is closely related to computational statistics, which focuses on making predictions using computers. Data mining is actually a field within machine learning, focusing on exploratory data analysis through unsupervised learning. Machine learning focuses on prediction based on known properties, but data mining focuses on discovery of previously unknown properties, as I explained before about data mining. So, descriptive analysis. Provide a simple summary about data that you have and about observations that you've made. So if we have some data that shows that it rained on Monday, rained on Tuesday, rained on Wednesday, rained on Thursday, how would we describe the weather for those 4 days? We'd probably say that it looked like it was raining. So we've created a description. Now, summaries can be in the form of an initial description, or they might be part of a small investigation. And I've put an example here. Shooting percentage in football is a descriptive statistic that summarizes the performance of a player. So how many goals did they score versus how many shots did they take at the goal? Okay, so we can do a descriptive statistic about that. They took 10 shots, they scored 1 goal. Regression analysis. So we're going to look at regression analysis in a little bit more detail later on in this course. But regression analysis is a set of statistical processes for estimating the relationship between a dependent variable and an independent variable. Now, there is a type where we can have multiple independent variables. These are called covariates. The most common form is a linear regression analysis. And we're going to look at doing a linear regression analysis in a later part of this course. So for example, have a look at this graph here. We have all these data points, and what this red line is this is a best fit line here. Now, to try and simplify this a little bit, if I said to you that I went to the co-op on Monday and I bought 1 apple, then I went to the co-op on Tuesday and I bought 2 apples, then I went to the co-op on Wednesday and I bought 3 apples, then I went to the co-op on Thursday and I bought 4 apples. Could you do an analysis on the previous data set to figure out how many apples I'm going to buy on Friday? Okay, so if you imagine we would have along the bottom days, Monday, Tuesday, Wednesday, Thursday. Let's change those to numbers. 1, 2, 3, 4, 5. Then we have apples up here. Let's change those to numbers. 1, 2, 3, 4, 5. So on Monday, I bought 1. Tuesday, I bought 2. Wednesday, I bought 3. Thursday, I bought 4. If we draw a line through those data points, we can likely predict the trend and thus position a point on the line that we think I'm going to use on Friday. So that's how we do a regression analysis. We go through existing data to try and find out what we think is going to happen. Now, here's a couple of graphics that I found that just describe some different types of analysis. So descriptive, exploratory, predictive, and inferential analysis. And then in this one, we have a graph that shows the complexity along the bottom here and the value up here. So we can see descriptive analysis or descriptive analytics has relatively low complexity, but also relatively low value. So just looking at statistics and saying what's happened is descriptive analysis. So moving up to some diagnostic analysis and then predictive and then prescriptive. Okay, so as the complexity of the analysis increases, so does the value that that analysis returns. So here is a summary of the 4 A's of data for this course. Data architecture is the routing and organizing of data. Data acquisition is getting data in from outside of the organization. Data archiving is storage for future reuse and anticipating that use. And the most detailed one of the 4 is data analysis, which is using models to create insights. And that is topic 2. Those are the 4 A's of data. So I'll stop the recording now, see if anyone wants to ask any questions, and then we can look at the practical for today. So this is just my RStudio server here. Just let me sign in just now to this, and we'll look at the contents of Lab 3. So let's close that one down. All right, so in Lab 3, we're going to be looking at text visualizations. Okay, and if we were American, we would use the letter Z here, or as Americans would call it, a Z. So what are we looking at? Well, some of you might be familiar with a concept called 6 degrees of separation. And this is a concept whereby, let me just get the definition. 6, let's do 6 degrees of separation. Let's do. Okay, so 6 degrees of separation is a concept, an idea that all people have on average 6 or fewer social connections away from each other. Okay, so if we think about it, you know me, okay? So if you imagine this being you, this being me, and this being my brother. So you over here don't know my brother, but through me, okay, you have 2 degrees of separation, or maybe even 1 degree of separation, I suppose, of this one. 2 degrees of separation to my brother. Now, you don't know the people that work with my brother in his job who would be here, but through my brother, through me to you, we do. Okay, let's just put little notches in there. So there's a theory that everyone has 6 or fewer social connections away from everyone else. So we all know each other, and so everyone that you're friends with and related to is connected to me in that way through you. Okay, so there's a kind of amusing take on this called 6 Degrees of Kevin Bacon. And 6 Degrees of Kevin Bacon is an idea that all actors in some way, and the people in Hollywood are in some way linked to Kevin Bacon, okay, via some other person or directly. So consider the film, maybe you've seen the film Apollo 13. There's also Forrest Gump, and there's a film called The Rock as well. Now, Tom Hanks has a Bacon score of 1 because he was in Apollo 13 with Kevin Bacon. So Kevin Bacon was in Apollo 13, so was Tom Hanks. Now, Ed Harris was also in Apollo 13, and Ed Harris was also in The Rock. Sean Connery was in The Rock, so he has a Bacon score of 2 because through Ed Harris, he has 2 degrees of separation from Kevin Bacon. So if you imagine Kevin Bacon being here, here's Ed Harris, here's Sean Connery here, okay, and here is if we do a little line out here, all right, this would be Nicolas Cage, because Nicolas Cage was in The Rock as well. So through Ed Harris, we have this separation here. Okay, so if any actor was in The Rock, they would come off here. So through any actor that was in a film with Sean Connery would be connected through Sean Connery, through Ed Harris, this way. Now, this is just a sort of humorous approach at looking at doing analysis, and these types of graphs here, okay, these types of plots, we have nodes, all right, which are, you can think of these as similar to network nodes, and we have links, all right, these things here. So very similar to in a network. And these are quite common types of graphics to use. And another way to think about this is if you imagine this as being the same as a routing network, okay, OSPF creates a similar type of topology as this, okay? So if you imagine here's your first router here, okay, and you're trying to send a packet to this router down here, okay, how does OSPF figure out the best way through? Okay, the answer we already know from the CCNA is that each of these has a weighting, so that might be worth 40 and that might be worth 10, but this one's worth 1, so would actually be better, going this way and then this way and then down here and then out to here or something. So we can use these types of layouts. Now, this type of design is called a social network analysis. Okay, now it's different from a kind of an analysis of social network data. Okay, a kind of an analysis of posts from social networks as we know them today. This is to do with the relationship between different points. Now, to do this, we need to import a library into R, a free library called iGraph. Okay, so this is iGraph's package page here, and we can get, look, it's in active development just now. An iGraph allows us to generate, okay, a lot of different visualizations. So we install the iGraph R package just by doing, in our RStudio server, we would just do, let me grab a new R script here. We would just do install.packages, and then remember to put it in quotes, iGraph, okay? And then to load up the library, we just type library, and then in there, iGraph. Once it's been installed, we just load it again. And remember, to run each line in R, we just do hold down Control and press return. Or if you were on an Apple computer, I think it would be Command return. So, right, so what we're going to do is we're going to download from the Moodle page two files. And those files are movies.csv and actors.csv. So let me just grab the Moodle page up here. Classes, we want this one. So, right, so we've made available two files here, actors and movies. I'll let you see what one of those looks like just now. I wonder if the browser can open a CSV file. Unlikely. I thought it might be able to display it, but it's fine. So it's a simple file. It's not a particularly complicated file. Here it is in my LibreOffice Calc. Let's just find the window, move this over here. Okay, so this is movies.csv. So you can see there's actors here, actor 1, actor 2, and the movie that they were in. Okay, and this task's actually been adapted from an exercise that I found online. I've changed the files just slightly. So we're going to import these two CSV files into R. Now, to do this, okay, we need to create a variable called movies, and we need to use the assignment operator, and we need to use read CSV, and we need to pass it the CSV. But before we do that, we need to tell R the working directory we're in. Okay, and we can do that by doing set working directory. So you need to tell R what folder this is in first before you can just tell it to load it as a variable here. Okay, once you've done that, you should be able to use head to recall the top, well, in this case, the top 16 items. Okay, head on actors will, by default, will recall the top 6 rows in the data set. Okay, then we're going to create a graph object, and we're going to plot it, and it's going to come out looking something like this. Okay, so we're going to see the link between these different actors, okay, and how they're related. And that is the first part. And then we're just going to make some changes to that graph by adding some extra arguments to the function to customize it a little bit. So that's part one of the lab. The second part is
Michael,
creating...
Could you go back to the graph?
Yeah, sure.
Why between Tom Hanks and Gary, there is 2 lines?
Between Tom Hanks and Gary, there's 2 lines. Ah, because I think they've been in 2 different films together. If we jump back over here, we should be able to see there, we're in Forrest Gump. And let's see where the other one is. Yeah, and in Apollo 13. See that? So that's why there's 2 lines there. You might know this chap from, I think he's in 24. 24, I think. And obviously you'll know Tom Hanks from Forrest Gump. So R will generate this, and we're going to do some customizations on it using some of these parameters. So that's the first part. Hopefully you can get in and have a look at that. Then word cloud generation. So we need to install quite a few packages to get this to work. But it's just a case of typing install.packages and the package we want. Okay, then all we do is we load that package using the library command. Okay, this exact package here, we just type library and put it there, and it'll load each one into R. Then we're going to use the same technique as before. We're going to load a file called scotland.txt. Now this must be specific to your particular system. So, you know, your username's unlikely to be username. If your name's John, then it's going to be something like see this PC John. This is just an example path.
Okay, I was going to ask that.
You're going to ask, right? So that's why I've put it in red. It's just an example path. You will need to change that to your actual path. So then if we go to, let me close down iGraph. Okay, I think I've got an example of this running somewhere in here. Yeah, so there you go. There's that load there. So for example, I have a folder called Home Michael R. All right, and if we go over to Files and go up, so yeah, there we are. We're in Home Michael R. Although it just says Home R, there's a Michael in the middle there because that's my username. And I can load scotland.txt. And remember, to load stuff in R, you just click on the line and press Control Return. All right, look, it's just loading it like that. Okay, so then all we're going to do is we're going to run this through some different data processing steps. The first one, we're going to take the docs or create a variable called docs. All right, and we're going to pass into that variable the text variable that we read in the file with up here. Okay, so here's text getting passed into the text here. From here is getting passed into this docs. Okay, now we're going to take docs, okay, and we're going to run another function on it, tmmap. Think of this as text map, okay, and we're going to transform it to lower. So we're going to make everything lowercase. I should say scotland.txt is a file I made that's got all of the text from the Wikipedia page about Scotland on it. Okay, so it's I went to Wikipedia and I copied the whole page about Scotland to a text file and saved it as scotland.txt. So that's the first thing we're going to do. The next kind of stage we're going to go through, we're going to run it through remove numbers. This will take away any numbers because we're only interested in the text. Then we're going to remove something called stop words. Okay, now stop words are words that we're not really going to get that much value from. So I once did a text analysis on the Lord of the Rings, and I can tell you that the most common word in the Lord of the Rings is the. So that doesn't really tell us that much. So stop words in, say, French would be like le, la, les. Okay, we're not that interested in the. Okay, el, la, ellos, okay, ellas, usted, tu. So we can take away things like the, this, said, like, now, to make our analysis a bit more meaningful. Okay, there's no point in me telling you that the most common word about Scotland is the. Okay, that doesn't really help us too much. So those are called stop words, and we can remove them with the function remove words, creating a little vector there with the concatenate C. Then we're going to remove punctuation, strip the white space. Now, this stage here is a little bit more complex, so just follow this through line by line. And what this is going to do is allow us to run these commands here. Now, this first command, find frequency, okay, will actually allow us to show what the most popular words are. And then this command will let us create a bar plot of that frequency. Now, just see if we can get that to run at the moment. Let's go for find frequency. I should have it here somewhere. Let me go pop this in here. So let's just clear that terminal off. Let's go back to our viewer and let's do find frequency in here. So I should have run in the Scotland.txt, but what I'll do is I'll just quickly run through this again to make sure it's in, pressing Control and Enter just to run the values into R again. So find frequency. All right, so look, here we go. We can see down in our viewer, down here, let's do, I think it's Control-Alt-1, Control-Alt-Shift-1, Alt-Shift-1, Control-Shift-1, Control-Shift-2. Okay, so there we go. So here are the most frequent words that appear about Scotland. Okay, things like Scotland, Scottish, Parliament, Kingdom, Monarch, Upland. Okay, so then what we're going to do is we're going to create a bar plot of these frequent words. So let me just jump back to a fuller view and let's put in our bar plot here. Okay, and let's go. All right, so there we go. So this is creating a bar plot. And as I said earlier, the most common word about Scotland, according to this file, is and. All right, so what we might want to do is revisit the stop words and take away and. All right, and let's make and. Let's put and in here. Okay, hang on. And. We don't care about and. Let's think that should be okay. Let's just pop the quotes into there. And let's go run that again. Right, so that's a bit better. And we could strip away was and for and things to try and generate this. Now, what we can do with this, okay, is we can use this to create some sort of a word cloud. And I've provided you with 3 examples on how to do this. So the first one is using a package called Word Cloud 2, just with a demo frequency to show you what a word cloud looks like that comes out of R. So running that, if we were to do so Control-Alt-4, Control-Alt-3, and let's go to the viewer here. All right, so this generates this word cloud. This is just with a demo frequency of words that this is being generated. All right, the demo frequency is about OPEC nations on Word Cloud 2, but to do an analysis on the Scotland text file, here we can run that now. So there we go. There's a word cloud coming out there, being generated. So that's what we're going to do in Lab 3. Okay, and if I go back to the Moodle page, I'll just show you what to add to the ePortfolio this week. So a screenshot of the head command for part 1.4 of the lab, a finalized plot from part 1.8, one of the word clouds. And then what I want you to do is go online and find a news or a magazine article, okay, and convert the article to a text file and use that to create a word cloud of that text file. Now, what is quite handy, I don't know if anyone's ever used this before, is in Firefox. Now, I know there will be similar things for Chrome, for example, but let me just open up Firefox, okay? In Firefox, let's say, okay, I want to find an article that's about ferrets, okay? Here is the Wikipedia page about ferrets. Well, let's find a... Okay, so let's say I wanted to convert this to a text file. Firefox has this very handy button up here, okay, called Reader Mode, and it looks like a little book. Now, if I click on Reader Mode, that's going to turn this into a much easier file to convert to text. Okay, so I don't normally use Firefox, but this is a very helpful. There's a Putorius file. Looks like a happy ferret there. So there we go. So that's Lab 3 there. I'm going to stop talking now, see if anyone wants to ask any questions about that. I'll stop the recording. Hopefully that's enough information.